Hello, Morgan Labs. We're finding spring constant, amplitude, general equation. This is under the bigger heading of waves, simple harmonic motion. Let me make it red. Simple harmonic motion. So what we have a spring, a 20 kilogram spring that's vibrating with a period of 18 seconds. That means one cycle is 18 seconds. The free end has a max velocity of 23 meters per second. Now, a lot of times when you have a wave or a spring constant type problem, they give you a force and a distance. That's not this problem. This problem, you have to use another equation because it gives you a max velocity, and then you have to figure it out another way. Like I said before, we're going to find the spring constant K, and then from that we can use it to find the amplitude B, and then C. We put it all together in a general equation. We'll assume our phase angle is 0. We're just talking about kind of one thing. Usually when you're talking about phase angles, you have two different things kind of going on, and you're trying to get a relationship between two oscillating things. So anyway, phase angle 0. Find spring constant K. Let's do that. Whoop. Step 1, we want the constant K. Step 2, what equations link our knowns and unknowns? We know the mass of this spring, we know the period, we know the max velocity. Our unknown is K. So what equations do we know that link all of these knowns and unknowns? This is the basic kind of two-step procedure. I remember in dynamics we had at Auburn, it was like a 4 or 5 step procedure, but two-step procedure, that'll get you there. Anyway, we'll get into more detail. You'll need more steps later on. Natural frequency, omega is square root of K over M. This is the basic kind of natural frequency kind of thing that you learn when you're talking about resonance and things vibrating. There are probably other kind of equations that relate your mass and your stiffness, but this is the most basic that you learn. And you also know that your omega, that's your angular frequency, is 1 over your period. Period is just how long it takes to do one cycle. So you flip that and you have so many cycles per second, or hertz, right? But we don't want hertz, we want the radians per second, which I think they're the same. I'll have to look it up to be sure, but I think they're the same. Okay, let's put these two together. This is kind of like a two equation deep kind of problem. So we kind of put these two together and we get 1 revolution over 18 seconds is square root of K over M. We have to convert it to radians per second for everything to work. That's another part of these physics problems. Look at the units. Make sure the units are proper, right? Newtons, meters, kilograms, seconds, if you're talking metric. If you're talking English, it depends. Inches, and then you have the G sub C constant. Anyway, we'll go over that when we get to it, when we get to a one with like English units, foot, pounds, all that. 1 revolution per 18 seconds. We're doing the kind of like the dimensional kind of analysis thing here. So what we do is we say, okay, we want to cancel out revolutions, but we want to put in its place radians. So you put the revolutions in the bottom, so the revolutions cancel, and you say there's 2 pi radians per revolution, right? And so you multiply everything out, 6.28 over 18, you get 0.349 radians per second. That is your omega, okay? Now another kind of step, I guess you would say step 3, reread your question. What do they want? What do they want? It's almost like step one. Do they want omega? Because a lot of times you'll be kind of stuck just in this kind of analysis mode and you forget, what do they actually want? They don't want omega. We're trying to get K. Remember, it's a two-step kind of equation kind of problem. So anyway, we go down, we say 0.349 is square root of K over M. Using a kind of simple kind of algebra thing, you can just say square root in the top and the bottom. It gives you the same thing. Just algebra is kind of simple because sometimes you can just plug in numbers and kind of test out kind of what you're thinking. But anyway, that's a property of exponents. So you go down to the next and we do a little algebra. We want the square root of M to be on the left-hand side. So you multiply both sides by square root of M. Square root of M cancels on the right-hand side, and you get this. I skipped a few steps, but I kind of said it what the steps were verbally. All right, so here we go. Keep going. We know the mass is 20 kilograms. No unit changes. All we need kilograms, meters, seconds, newtons, like that. So don't have to change anything on this one. So you get your calculator out. 0.349 times square root of 20 is 1.560, and that equals the square root of your spring constant. You can do this in your head. Well, you can make an estimate, right? If you didn't have a calculator, you would say, what's close to 20? That's like 16. So square root of 16 is 4. What's the next one up? It's 25. So that square root of 20 is somewhere in between 4 and 5. And then you say something like maybe 4.2 times 0.349, kind of get an estimate. That's just a bonus there, how to estimate when you have square roots. Okay, let's go up. Next step. So we square both sides to get rid of the square root. It's 2.436 newtons per meter. That's our spring constant. We have answer A. I didn't mean to do that. Let me go here. Okay, there you go, like that. Okay, there you go. B, now we find the amplitude. So now we have the spring constant. That's going to help us in our next equation find the amplitude. Big concept. Okay, so that's step one. We want the amplitude. We want the amplitude. Step two, knowns and unknowns. Okay, what? We have spring constant. We have A. What equations or concepts do we use to solve? Okay, we know kinetic energy. That'll be 1/2 mv squared. We have the V, right? We have the velocity and the spring potential. We have the spring constant. So it's okay. So it looks like we can kind of use this concept of kinetic energy equaling the spring potential. May not be when you're in the real world. This is like an estimate because you have friction and everything else kind of coming into play. But this is a good start. Okay, let's go to the next. Kinetic energy equals the spring energy. That's what we said. So kinetic energy is 1/2 mv squared, or Vmax squared, and your spring energy, the potential energy, is 1/2 kx squared. It's kind of similar kind of setup, right, in the variables. So should be easy to remember spring energy and kinetic energy. But the thing here is at your max velocity, that's going to be where you have your max amplitude. The max stretch, you think of a spring vibrating back and forth. At that max point, it's going to have your max amplitude. So here we go. Plug everything in. It's just a straight plug in. Now make sure you have all your units okay. Make sure you have your calculator in degrees. If you do like maybe a trig or something. We're not doing any trig. But anyway, make sure your calculator set up okay and go for it. So it's 1/2 20 times 23. Oh man. Okay, 1/2 20 times 23 squared, and then so okay, I have to redo this one. Somebody sent me a text. Anyway, you do all this, and then it's almost like when you're doing a show. It's like closed set, right? You gotta turn the phone off. Turn your phone to airplane mode when you're doing videos on your phone or on your tablet. Anyway, so here we go. 5,290 equals 1/2 or 0.5 times 1.56a squared. And then what we have here, we go down. So 5,290 equals 0.780a squared. You divide said 0.78 on both sides, you get a squared. 6,782 equals a squared. The amplitude is 82.4. Whew, done. So now we're almost there. We've done part B. Part C, general equation. All we have to do is put everything together. Step 1, they want the general equation. Step 2, what equation is the general equation? And that would be this here. One big part of these physics problems, the algebra-based ones, or the calculus-based too, is just finding your equation that links everything, right? It just gets harder when you have like the two equations. You have to kind of mix and match. When you start mixing and matching equations, it gets kind of hairy. But after you do it for a while, you know, it's not too hard. Just like we did at the beginning. All right, so we have that, and then so yeah, we just plug everything in. X of t, which means your function with respect to t, is A amplitude times sine omega t plus phi. Phase angle is 0. We're not talking about two different kind of things, two different waves going on. So in the end, you should get 82.4 sine of 0.349 t. Now, 82.4 is amplitude for a spring, maybe a little much, but a lot of times we can assume that something acts like as if it were a spring. So this could be a system that's 20 kilograms with like little gadgets and gizmos and whatever, this big kind of mechanical kind of assembly that has a natural frequency of 0.349. And it's like, you know, the displacement could be, you know, it doesn't have to be like a stretch of a spring. It could be other things. You see what I'm saying? So when we talk about springs and dampers and things like that, it's just kind of a way to simplify more complicated things in the real world. So anyway, if you had a physics problem and they just wanted you to do these simple things, you have all the steps. Good luck. I'll see if I can make another video without somebody sent me a text or whatever. I'll see if I can take that out and put the notes. I'll put the notes in my website, and if you need them, you can just you can download them. Hope you learned something. Morgan Labs.